We're going to switch gears here a little bit, but I'm very grateful for the context, the background that Chuck provided about critical minerals and rare earth elements, because that'll be a theme in my talk as well. Although I'm listed here in the schedule as the presenter, this is work that was done by a large team of people, and I just want to mention a few of them here. So the team members listed first are from Pacific Northwest National Lab. We also had a group from Rutgers University Newark helping with ground-based geophysics. And I want also to credit the support and assistance we had from the Pennsylvania DEP and from the EPA, especially Bet Conway, Dan Corey, and Jim Andrews, who are here in the audience today too. So this was a large team effort. Okay, I'm going to be talking about drone-based electromagnetic imaging. So we're going to be looking underground with geophysical techniques. These techniques are used widely for mineral exploration. They're used from airborne platforms, helicopter and fixed wing. They're used ground-based platforms, also marine platforms. So we tow these instruments behind boats, behind planes, under helicopters, and collect data to see underground, to see what's there, to do geologic mapping and understand the depth to bedrock, what the bedrock is, depth to water table, and so forth. The talk that I'll deliver here is going to go over first objectives, some instrumentation that we're developing on the project, high-performance computing capabilities that we bring to bear on this problem, AI-based inversion and classification, so we're using deep learning tools to speed up the data analysis. Cloud-based processing, a lot of this happens in the cloud so that we can deliver results to people in the field in near real time. And then finally a field demonstration, which was more of a field scale test at several sites in Shamokin. The overarching goal here is to develop and integrate and demonstrate new drone-based geophysical imaging and remote sensing to quantify critical minerals in various feedstocks, as we call them. And although we're talking today about Shamokin and about coal mine refuse, these techniques have broad applicability to tailings piles, impoundments, and other feedstocks that we're looking at for critical mineral production in the US. So as Chuck alluded to, we've found ourselves here in the United States in a state where our supply chain is really at risk, and it's perceived now to be a national security issue that we are not producing critical minerals in this country like we were, and we're relying on other countries that we're not always in agreement with for access to critical minerals and also for processing. Even the critical minerals that we produce in this country that we mine, much of that is sent abroad for processing and then returned. So there are real supply chain risks associated with this. It's unlikely that we're going to see huge mines permitted again, like Kennecott and so forth, where a lot of copper is produced. Mines take a long time to permit. And we've probably found all the really large Kennecott scale mines in this country, at least in the continental US. So we need to look at smaller resources, smaller scale, and unconventional ones. Again, impoundments, tailings piles, mine refuse. And Chuck made a strong case there that there's a lot of rare earth elements locked up in these rocks. If we're going to make this something that's feasible, we're going to need to take what we're using for geologic exploration, for critical minerals, and downscale it, make it higher resolution for these smaller scale deposits and for these unconventional feedstocks. And we're going to need to help accelerate the time frame for doing the characterization and the extraction, because the margins on these are not going to be what they are on existing large-scale mining operations. So our technical objectives are to demonstrate these new techniques to capitalize on drone-based technology for this, to speed it up, to make it cheaper, to be able to do this in areas where it might not be practical to go with helicopters, fixed wing, at the resolution that we need. We're developing codes and processing workflows for real-time geophysical inversion. When I talk about inversion, it's basically the process of producing an image from the data that we collect. So this is a lot like medical, I'm sorry for the mic going in and out. This is a lot like medical imaging in concept, but applied to the Earth. And sometimes we're using the same physics as used in medical imaging. The codes and processing workflows are being integrated with remote sensing data. So we're trying to get this draped image of the underground alongside imaging of the surface. And we'll talk a little bit about that too. So at right, you see a schematic for how this is conceived as working. We can either have transmitters on the ground, which is kind of conventional, and that's what we would use for deep scale imaging. You can have a grounded dipole antenna where you're driving current into the ground, and that's shown here. Or we can have a transmitter that is in the air or maybe hopping around with a coil transmitter using EM induction rather than direct coupling to the Earth. And then we have a receiver, or we could have swarms of receivers flying around collecting data as the transmitter is operating. Just a little bit of context for doing this. Again, we've been using ground-based geophysics and airborne geophysics for many decades. Ground-based geophysics goes back about 100 years now to the Schlumberger brothers, who were the founders of Schlumberger that you may have heard of for mineral exploration and also more these days for oil and gas reservoir characterization and operations. We see drone-based geophysics as filling important gaps between ground and airborne and satellite with respect to spatial data coverage and also the resolution and the ability to repeat measurements over time. The premises here are that airborne geophysics is widely and effectively used, but the delivery times are on the order of weeks to months, and they're very prone to problems around existing metallic infrastructure. These techniques are usually used in pristine areas where there's not a lot of stuff on the ground. So you're not exploring for mineral resources around New York City or around even places like Pittsburgh. We need techniques that we can use in those environments. So we're going to account for metallic infrastructure in a lot of our modeling and data analysis to relax the problems associated with doing geophysics around those. The costs associated with doing repeat surveys are enormous. So the mobilization costs for airborne geophysics can be on the order of $50,000 to $100,000 just to get the system to your site to start the characterization. Many of the papers on the mine of the future talk about digital twins and real-time sensing and having a digital mine where data is continuously being fed into some system that's making sense of it, that's visualizing it, that's allowing you to predict the mine operation and what your extractions will yield. So for this, we need to be able to do repeat measurements. And that's, again, something that's very achievable with drones and not so much with helicopters and fixed-wing platforms. So we're doing this to integrate geophysics with other data types like hyperspectral imaging or chemical measurements, XRF, XRD, whatever you have in the field. And all that should feed into the same platform. So our specific project has a few different components to it. We're developing codes for autonomous workflows, new simulation capabilities, and AI-based processing to speed everything up. And we're not just using AI here for AI's sake, because that's what everybody's doing. This is a problem where we really need to be able to speed up the data analysis. Data analysis for geophysics, typically, again, weeks to months to deliver results to people to make decisions for. That's not going to work for the mine of the future, and it's also very expensive. Drone-based data acquisition for the reasons I've discussed, reducing costs, labor, and being able to repeat measurements. At a mine that's actively operating, you could have drones missioned to operate, do surveys, repeat schedule, say every Monday. As you peel away layers of rock, or tailings or mine refuse, you get better resolution with those repeat surveys because you've cleared away what was above, and that's also information to help calibrate your interpretation if you're using AI. Multi-sensor fusion, again, we want to bring together different data types within the same framework, and cloud-based architecture for delivering results to the field using tools like augmented reality. All right, so we want to be able to do this a few different ways, as I alluded to before. We could have a single drone operating with a receiver and a transmitter on it, and this is done. This is done in practice. There are tools that we can use in the field that you can carry around. People have begun flying those with drones. The challenge here, the issue, the limitation is that this can only see so deep. When you have the transmitter and receiver in a small unit like this, and they're close together, there are some limitations on how deep you can see and also on resolution. When transmitters are on the ground, you can see very deep, but of course that's problematic because you have to move it around to see elsewhere. If the transmitter is flying or hopping around, that's better because we can cover more ground and we can do it cheaply, and we could have multiple receivers potentially. Now, separating the transmitter and receiver is one of the major advances in the work that I'm going to describe. There are a lot of issues in the electronics that I won't dig into, but divorcing them, separating them, is a challenge with respect to instrumentation, and it's one we've overcome on this project. So with drone-to-drone EM surveys, we can start to see maybe up to depths of 100 to 200 meters. This is similar to some helicopter airborne techniques. Surface to drone, again, where you have the transmitter on the ground, that's more like geologic exploration where you can see 2 to 3 kilometers deep. And we can use all three configurations in the software that we've developed and potentially also with the instrumentation that we're developing. So with the instrumentation developments, we've cut the umbilical, as it's referred to, between the transmitter and the receiver. We've used blue technology, so that's technology sourced only from the United States. There's a lot of issues with using certain foreign drone platforms for government work, and we've got around that by starting from scratch and making our own instrumentation. The receiver unit has been deployed on drones in Shamokin in our field test. The transmitter unit thus far has only been deployed on the ground. It's still a little bit bulky. We're in the process of miniaturizing those electronics. In the past, this is what frequency domain EM data collection looked like. You see, actually this is a time domain system, but it's similar in concept. You've got a transmitter here, one person is holding, the receiver's over here, and you've got this cord in between that's handling all the electronics and the communication. This is what our system looks like in the field. We'll have some more on it later. This was in an earlier field test in Washington State where the transmitter was just on the ground and the receiver roved around on a cart before we put it in the air. This is what the laptop looks like with the interface. So we're getting results in real time in the field, and these are just some of the photos of fabricating the EM coils for the transmitter and receiver. The receiver unit looks like this. So we've got the coil here. It's housed in this, this enclosure and suspended below the drone. We played around with the offset between the drone and the receiver to make sure there wasn't interference with the electronics and the props, also too much swaying. So we have nav and GPS, differential GPS on the receiver separate from what's on the drone so that we at all times know its orientation and location. It's got a longer stilt on one leg here so that when it falls, it kind of collapses to the side and stays away from the props. I won't get it too much into the electronics here, but again, this was all just developed in-house so that we can have total control over the instrumentation and tune it for the frequencies and the depth ranges we're interested in. The transmitter here transmits at 4 different frequencies, and there's a manual switch so that it kind of toggles between those. Each frequency is effectively giving you information at a different depth into the Earth. So some key advances here are that there's no physical connection between the transmitter and receiver. This can be done in fully airborne or semi-airborne mode. And we've demonstrated in the semi-airborne where the receiver is flying and the transmitter is on the ground. It's again multi-frequency, so in principle here we can see with the power transmitter we're using to tens of meters depth. That could be improved if we used a more powerful transmitter, but for now we're probably limited to upwards of 100 meters depending on the site. And again, there's potential for deeper imaging with a grounded dipole antenna that could be integrated into this in the future. We've only used one receiver on a drone at this point, but there's no limitation on that. We could have swarms of receivers flying around for more efficiency, and that's one of the reasons that we're using drones for this again. We've been developing computational tools for the data analysis. So traditionally, the data analysis for EM imaging is done with at least at PNNL, is done with high performance computing. So we're using very large computers, supercomputers, solving Maxwell's equations in 3D for the electromagnetic problem, and doing that repeatedly with an optimization procedure, and this again is what we refer to as inversion, to produce a 3D image of the subsurface. The raw data that we collect are just, as you see here, basically in phase and out of phase components of the data. So we're collecting information that's hard to interpret visually before you do the imaging problem, before you analyze the data to produce the subsurface image. So if, just for a hypothetical example, if we had a subsurface model, this is a vertical slice into the earth with these different electrical resistivities, this is the image that would result from that. And with geophysics, I try to remind people that we never see into the subsurface with Superman-like X-ray vision. It's never 20/20 vision of the subsurface. Everything's kind of blurry and blunted, and that's because the physics just loses information. It's not providing the same level of information that you can achieve with medical imaging, where you can move antennas or sensors, transmitters, receivers, electrodes all the way around your target, the human body or whatever part you're trying to image. So if you've ever done an MRI, you go into kind of a tunnel and sensors are rotating, transmitters constantly collecting more and more data. Same thing with a CAT scan. With the Earth, we're really only able to access typically the top unless we also put sensors down well, but we can never put sensors down at the bottom of the imaging. So we get this blurring and blunting that occurs. But this image, constructing that image, is a very large computational problem to solve. We have these tools at PNNL. One of the codes we use and develop is called pGemini. Again, it's a Maxwell's equation solver. We've extended the capabilities of pGemini on this project to support the drone-based data acquisition geometries and to be able to use data from swarms of receivers simultaneously. We've also been developing tools within it to account for metallic infrastructure. So if you're doing this near a railroad track or near a steel-cased well, we can account for that in the modeling. And the HPC tools are nowhere near real time. These take, even on high-performance computers, sometimes days to solve the inverse problem. This is just a quick example, though, using pGemini to try to image these two different targets, and it doesn't matter what they are, but these are just resistivity features in the subsurface. And so we can fly drones around with receivers at various offsets and orientations from the transmitter, collect the data, and then do the inversion. And these are just a couple examples of what the inversions look like with different drone geometries and different geologic features in the subsurface. So you could, perhaps you're looking for fault blocks and trying to understand geologic structure or an anticline or whatnot, and you're looking at some fold. These are how they would manifest in the inverted model. Again, it's not a perfect 20/20 vision of the subsurface. It's somewhat blurry and blunted. So this is using high-performance computing tools that take, again, hours, days, or sometimes even weeks to solve those problems. We've been training deep learning algorithms to this process to speed this up by orders of magnitude. And we've got this now to the point where these deep learning neural networks can solve the same problem approximately in seconds, or a fraction of a second in some cases. So I'm not going to dig into this too much, but this is very exciting. I wouldn't say that this is the final result that we would always rely on. We still use the high-performance computing tools, but if you need a quick, I won't call it dirty, but if you need a quick result in the field to make decisions around, while you're still in the field, this is the way to go. And these are just some more examples, 2D cross-sections of electrical properties, and we take some slices through them and look at the true resistivity and the inverted resistivity. And we do this with the AI in this case, and it's doing very well compared to what's really there. And in the interest of time, I'll skip through this a little bit quickly, but it's basically the same story, that the AI tools for these problems, once trained to hundreds of thousands of models generated with the high-performance computing tool, we can then perform these inversions in milliseconds. We've been developing also tools for hyperspectral data analysis. Hyperspectral imaging can be done from drones, it can be done from satellites, and it is one of the most direct ways that we can try to map mineralogy in the field remotely. So some of you will be familiar with handheld XRF, which the EPA was doing around Shamokin, with XRD, which is more often done in the lab, but there are portable XRDs you can take to the field. Hyperspectral imaging allows you to look at the EM spectra that's reflected off of a surface and analyze that spectrum for unique characteristics that can tell you about mineralogy. This is not so easily done when you've got mixtures of minerals or when there's vegetative cover and so forth, but I think there's enormous potential to use this in places where you've got mine tailings, you've got mine refuse, and so forth. So we've been training not for a regression problem or estimation problem as in the last slides. We've been training these deep learning algorithms to try to interpret hyperspectral data for mineralogy. And this I'm not going to dig into very much. It's another part of our overall project, and it's working very well. We've got this algorithm together that does a great job of speeding up that process so that we could analyze data in real time while it's being collected in the field. We have a software package that we've put together at PNNL called Pterodactyl for bringing all of these different data types together and managing it with GIS-like capabilities, and also doing statistics and visualization on the data that are collected. And so we're going to be getting in the next couple slides into the field test that we conducted in Shamokin. This is from that. This is what we were seeing in the software as we were collecting the data out there with Dan, Jim, and others. So we could see the drone path, and here the receiver was flying circles around the transmitter on the ground, and we'd move the transmitter and then collect another set of data around it. And the reason we were doing these circular surveys is that had a constant offset between the transmitter and the receiver. And so we had pre-trained the AI algorithm to data collected with certain geometries, and that just made it tractable. If we were trying to train the AI to any arbitrary geometry, we'd probably still be running the high-performance computing simulations to do that training. There would have been too many. So this is what the interface looks like. We've got visualizations. You can bring in DEM, topography. These are the data where the estimates are in the subsurface. So as the drone is flying, we're getting images, just 1D point clouds here underneath it of the conductivity into the earth. The field demonstration, I stole these photos from Bet. I hope that's okay. Not stealing too much thunder here, but many of you have been through Shamokin and seen it, and you've seen many slides yesterday, I think actually some of the same ones. I don't need to describe the sites to you very much at this point, but our interest here is rare earth elements. There's a legacy of anthracite mining in the region. We were coordinating our demonstration, our test effort with the Pennsylvania DEP, with NETL, with the EPA, USGS, Chuck Cravata as well. And then several universities were working there too, including Rutgers University Newark, who came out and provided ground geophysics for comparison to our airborne data. We conducted drone EM flights at 2 coal mine refuse sites that you'll know by the names of Cameron, Glen Burn, and Excelsior. And there's work in the region here by Chuck, as you saw in the last talk, going back decades, showing that there's rare earths in these materials and in the water that moves through them. So again, a lot of other data collection and efforts out there. I've mentioned these groups already. Also, I understand Lawrence Berkeley National Lab is headed for a field demonstration of their own. These are just some overhead snapshots from Google Earth. And I don't have a color scale on here, and I'm showing someone else's data, but I just want to make the point that there are other data types being collected that we can compare to in the future, and that's important. Geophysics is always indirect. We're not imaging mineralogy directly. Even with the hyperspectral, it's not truly direct. So we always need something to ground truth, or at least to calibrate our interpretations. Our targets here are things like the thickness of the pile, depth to where there might be water within it, understanding moisture distribution, understanding where the actual native material is underneath. But again, these techniques could be used at other sites for other purposes. We're interested in monitoring copper heap leaches, where material fluids are released or injected into piles of tailings to mobilize copper and move that through. So our purpose here was really the field demonstration more than site-specific characterization. And we conducted the drone flights with multi-frequency EM imaging. So these are just a couple of photos from one of the mine refuse sites. Hopefully you can see the drone in the air there and here as well. And another reason that drones, I think, are very valuable for these problems, especially in mining areas, is that here perhaps we could have walked or traipsed up here and collected data, but at many sites it would be very dangerous and would be problematic. So this takes people out of harm's way when you can be flying around instead of having people on the ground doing what you see here, which is our Rutgers crew. These are some students and a professor from Rutgers collecting the ground-based equivalents to what we were doing in the air. Much more slowly and with more labor involved. So we collected a number of different data types. I won't dig into too much except to just show this comparison. So this is ground-based geophysics, collected with both time domain EM, frequency domain EM, also electrical resistivity. And the EM and resistivity methods are put together here. And you can see a couple of things. You can see this more resistive layer up above, and then it gets a little bit more conductive. The ground-based geophysics that they did does not extend too deep. We'll see in the next slide, I think it goes down about 20 meters. Now, this is what we got with the airborne EM here, with both the physics-based inversion and the AI-based. And they're pretty similar. To compare to the ground-based results, so these are ground-based, and this is what we got with the drone. First off, the ground-based produced just 2D cross-sections. With the drone, we were able to produce 3D images. The ERT, the ground-based electrical resistivity in EM saw down about 20 meters. It was highly resistive in the upper 15 to 20, and then it became conductive. Now, with that method, you can only see down about 20 meters. With our approach, with the drone-based system, we were seeing down on the order of 50 or 60 meters. And we were able to see past where it becomes conductive to where it becomes resistive again. Now, the electrical conductivity, which is the reciprocal of resistivity in the earth, increases with fluid saturation, it increases with total dissolved solids. The conductivity decreases when you get into bedrock and more solid, less porous materials. So we interpret here that we've got fairly dry material up at the surface, increasingly moist, And then perhaps this is native material here underneath. So again, upper meter, moderate conductivity, likely moisture. You see that in a few spots. Increasingly resistive or lower conductivity to depths of about 20 meters. And then we get into a conductive layer and then back to resistive below. All right, so this is the last slide. At this stage in the project, we've got some publications and internal review. I hope to be able to share those with folks soon from DEP, EPA, and also the property owners. We're continuing to coordinate with those same groups, and we look forward to collaborating with them further. We will provide the data, as I just said, to the cooperators and stakeholders, and we're further refining the electronics for hopefully additional field demonstrations in the future. Great, thank you.